All right, last video for this chapter, density. So this is a property, specifically a physical property of matter that actually is most useful when used as a conversion factor. And what density is it is the mass of a thing divided by its volume. Now normally when we talk about densities, we're going to talk about a material density, so like a specific material has a certain density, but truthfully you could define a density for anything. It could even be a mixture of things and you could have a density. That's just usually not as useful. The more useful way of talking about density is to talk about a specific material. So some things have very high densities and some things have very low densities. But one thing we don't want to do is we do not want to confuse density and weight, or density and mass. Now they are related to each other, as you can see, because density is the mass divided by the volume, but just because something is dense does not mean that it's going to be heavy. And just because something has a low density does not necessarily mean that it is going to be light, because the mass is only half of that. It's only technically a third of the equation, but half of that one side of the equation. The other part is the volume. You could have a piece of lead that is the size of a BB, if you know what that is, just a little tiny pellet of lead, and that would not weigh much at all. Like you could feel it in your hand. It's not so small that you couldn't feel that it's there, but it would not weigh much at all just because it's so small. On the other hand, you could have a piece of styrofoam, which is very low density, especially compared to lead. Lead is extremely high density. But you could have a piece of styrofoam that is very low density, and if that piece of styrofoam was the size of a minivan, it would weigh a whole lot more than that pellet of lead, even though its density is much, much smaller. It's much lower density. Because again, the mass is only one half of that calculation. The volume is the other half. It's not just how much does it weigh, it's how much space is it occupying as well. So it's how much stuff is packed into how small of a space. That is the density. So water, for example, has the density of 1 gram per mil. And that's one of the nice things about the metric system, is that the density of water works out so nicely. Iron, on the other hand, is significantly more dense, specifically 7.87 times more dense. It has a density of 7.87 grams for every mil. So we could write this differently. We could say it's 7.87 grams per 1 mil. It's the same thing that we're saying there. It's the amount of mass for every 1 milliliter. So if we think about these densities, I want you to pause the video here for a second and answer these first two questions. Don't worry about the second two yet. We're just going to talk about the first two. So if we have equal volumes of water and iron, which one weighs more? And if we have equal masses, which one has a greater volume? So pause the video and think about those two questions and develop an answer for those. Alright, hopefully you stopped the video there and thought about that for a minute. So if we have equal volumes of water and iron, we could even, just to help us think about it, just pick a volume. Let's say a gallon. You know, we're used to having gallons of milk and things like that, so it's a volume that you're decently familiar with. So if we have a gallon of water, it's going to weigh about as much as a gallon of milk. It'll be a little bit less. Milk is slightly more dense just because there's stuff dissolved in the water, but not way more dense. So it would have about that weight. But now think about holding a gallon of iron. The iron's going to weigh more. If you have equal volumes, if you have the same volume of stuff, the thing that has the higher density is going to weigh more because there's more stuff packed in for every unit of volume. So then the opposite is going to be true for part B there, which if you have equal masses. So if you have a pound of water versus a pound of iron, to put it in units that you're more familiar with, the thing that's going to have the greater volume is going to be the water. It's going to take more water to get the same amount of mass. So it's going to take more of that stuff to get to that same mass. Whereas the iron, which is much more dense, you don't need as much. You don't need as large a volume to get to that mass. All right, so with that being said, let's look at the last two here. So go ahead and pause the video again and try to answer these last two questions. So these are calculation questions now. So how much does 6.44 mils of iron weigh? And what volume does 50 kilograms of iron weigh? So be thinking of this equation here. You can use this equation to solve both of those calculations, actually. But do keep in mind that this is kilograms. So go ahead and pause the video and try to work that out. All right, so for this first one here, we have 6.44 mils of iron, and we want to know the mass. We want to know how much it weighs. So there's kind of two different ways of doing this that are really the same, but they just kind of they feel different, even though they are actually the same. So we could use the density as a conversion factor. This is the way that I prefer to do it. And we could have 6.44 mils. It's the amount that we're trying to change from volume to mass. And we could just use the density as a conversion factor. So because we have iron, and we know the density of iron is 7.87 grams per mil, we can take this and we can plug it in just as is, because we want the mils to cancel out. So for every 1 mil, that is the same as 7.87 grams. And if we do that math, that is 50 point, and let's see, I get 3 sig figs there because each of them have 3 sig figs. So 50.7 is what that's going to work out to be, grams, because the milliliters cancel out. Now the other way, which is in reality is the same, but it feels different, is to go ahead and just use the density is equal to the mass divided by the volume equation. So you could take the density, plug that in here, so you would have 7.87 grams per mil is equal to the mass, which is what we're trying to solve for, divided by the volume, which is 6.44 mils. And so now you have an equation here with one unknown, and you can solve for the mass. Now again, this feels different, it looks different, but if you actually do the math, it's exactly the same, because you're going to end up just multiplying both of these together to get the mass, which is exactly what we did here. So it's the same process, it just looks and feels different. If this is much more comfortable for you, if you saw me doing this and you were like, what the heck is he doing? That doesn't make any sense at all. And then you saw me explain it this way and you're like, oh, that makes much more sense. Then just do it this way. It's fine. I don't care. To me, just personally, this makes sense to me, to treat the density as a conversion factor between mass and volume. But I understand that that doesn't make sense to some people, at least as much sense. So whichever way works best for you, just go for that. So then the last one here, 50 kilograms, how much volume does it occupy? So the hint that I gave you there was to realize that we have kilograms here. We need to convert that into grams. So 50 kilograms. Convert that into grams first. If you remember, 1 kilogram is the same, or sorry, 1 kilogram is the same as 1,000 grams. So that's going to be, and let's just write it in scientific notation. That's going to be 5.00 times 10 to the 4 grams. And so actually, why don't we go ahead and solve this the second way here. So the density is 7.87 grams per mil. We are trying to find the volume, And we know that the mass is 5.00 times 10 to the 4 grams. We're going to have a little bit more complicated algebra here. Don't make the mistake of just dividing both sides by the 50,000 grams and saying that's your answer, because that would give you 1 over the volume. So what we actually need to do is we're going to multiply both sides by V, by the volume. That would essentially just move the volume over this side, and then divide both sides by the 7.87, which would move it over here into the denominator. And so if we do that, and I wish I had space to write that out there, but hopefully that explanation made sense. So the 5 times 10 to the 4 divided by 7.87 gives us a volume of 6,000, and let's see, I only get 3 sig figs here. So 6,350 milliliters, which, by the way, would also be 6.35 liters. All right. That'll be it for those. So one last density question here before we can wrap this up. A man receives a platinum ring from his fiancée before the wedding. He notices that the ring feels a little light for its size and decides to determine its density. He places the ring on a balance and finds that it has a mass of 3.15 grams. He then finds that the ring displaces 0.233 cubic centimeters of water. Is the ring made of platinum? And actually, I don't think that page number is correct. I think that's, again, from an old book. But it's asking us to determine if this is actually made of platinum. And so to do that, we would have to look up the density of platinum, which I don't remember the exact number, but I do remember the result of this question. So we're going to go ahead and calculate the density first. So the density, remember, is the mass divided by the volume. And so all we're going to do here is just going to take the mass and divide by the volume. The one thing that might have been a little bit tricky here is if you didn't realize what was measured here was the volume. When it says that he finds that the ring displaces 0.233 cubic centimeters of water, it might not be immediately obvious that that is talking about the volume. But if you remember when we discussed derived units, we said that volumes are always distances cubed. So this is actually the same as milliliters. 1 centimeter cubed is the same as 1 milliliter. And so all we have to do to find the density is just take 3.15 grams and divide it by 0.233 centimeters cubed. And that is 13.51 grams per centimeter cubed. And if you go to the book and you look up the density for platinum, what you will find is that is not the density of platinum. It is a decent bit less. If I remember correctly, platinum is somewhere around 20, I think, grams per mil. But I could be wrong about that. But I know I am correct that this is not actually platinum. This does not match the density of platinum. So, unfortunately, this guy's fiancée got gypped. Either that or the fiancée intentionally got a cheap ring and just told him that it was platinum. Scandal. So scandalous. Anyway, moving on from that, one last quick thing here before we call it for the chapter. I do want to talk about accuracy versus precision. When we say that we have an accurate set of measurements, what we're saying is that our measurements are very, very close to the correct value, to the true value that we should have gotten. Now, sometimes it's not possible to get accurate measurements just because you actually don't even know what the correct value is. But if you know what the correct value should be, so if, for example, you're measuring the density of water, that is a known value, you know what you should get when you measure the density of water. And so you can comment on the accuracy because you know how close your measurements are to that correct value. When we talk about how precise a set of measurements are, what we're commenting on is how close the measurements are to each other. So you can have precise data that's not actually accurate. So if you make a measurement over and over and over, and you get essentially the same result, which is what we see here. So you're getting the same result, it's in the same area each time you do it. It doesn't necessarily mean that it's going to be where you want it to be. It's not necessarily going to be there in the bullseye. So you can have precision without accuracy. And usually when you have something like this, all you'll do, like if you have some kind of an instrument that you're using where you're getting the same result but it's not the result that you're expecting, usually that means like your instrument is misaligned or something like that. There's something that you can just kind of shift it. You just say, well, I keep getting this result here, so I'm just going to take this whole target and just kind of shift it up here so that now I'm getting the correct value there. That's usually what happens with instruments like that. Obviously, you can't do that in every case, but sometimes that is what happens. So that is accuracy versus precision. And one last quick thing here just about problem solving. If you do not have a system for solving problems as you work through the homework, this is the system that I use. And so I would encourage you to, at the very least, develop a system, some kind of system that you use as you're working through these questions. It doesn't have to be exactly the same as this one, but this is a system that I learned in college, and I thought it worked pretty well. So the overall way this works is you read through the problem all the way and read it through carefully. And I know that seems like, well, duh, you read the problem. But the important thing here is read through the problem carefully, because oftentimes you'll go into a problem with thinking that you know what the question is asking for. You think you know what's going to happen, you think you know what it's going to ask for, you think you know what it's going to give you, and so you just kind of skim through it and actually miss some important points. So read the question carefully, and then actually write down what you're looking for. So write down, I'm looking for the density. So if I'm working through a problem and I'm trying to find the density, I usually represent the density as a capital D, and so I would put density and question marks. So I'm looking for this, trying to find the density. So at that point then I'll think about, what do I know about the density? Do I know equations? Do I know any laws? Do I know conversion factors that are related to the density? And so I would write down, well, I know the density is equal to the mass times the volume, and if in the problem somewhere, like I had kilograms like I had before, then I would say, okay, kilograms, I know that, 1 kilogram is equal to 1,000 grams, so I'll probably have to do that. Like, just write down everything you know, everything that's related to the stuff that's given to you. Then, once you have everything that you know, so you have everything that was in the problem, you know what you're looking for, you know what you know about those things, now comes the math, essentially. Technically the math is the next part here, actually doing the math, but the working out the pathway from what you know to what you're trying to discover. So this can sometimes be the hardest part here, is I know what I'm looking for and I know what I have. Can I find the pathway from what I have to what I'm looking for? That's the tricky part sometimes. But usually this part is what students start with. They just skim through the problem and say, okay, I need to find the pathway. They don't take the time to read it carefully and make sure they understand what it's asking for, make sure they know what has been covered up to that point, all the equations and things like that. I think having that starting point helps when you get to this point to find that pathway. And so then the last part there is just actually doing the math. Plug it into the calculator, making sure you have the correct sig figs and all that good stuff. All right, so that is it for this chapter. If you have questions, feel free to email me about them or to chat with me about those. And I will see you all in Chapter 2.